Hello everyone, my name is Sergio Biagioni. Welcome to the MATLAB and Simulink video series for unmanned vehicle systems. Today we're going to talk about the most relevant topic in this video series, using MATLAB and Simulink for unmanned vehicle systems. Let's start with the first question. Why use MATLAB and Simulink for your unmanned vehicle system competition? Using MATLAB and Simulink, you can join the many engineers in industry that are currently using these tools to develop autonomous systems. MATLAB and Simulink provides one environment that can be used to design algorithms, model a vehicle, and deploy algorithms to hardware. MATLAB and Simulink also enables the use of model-based design, which is the use of a mathematical model of the system to design and deploy algorithms. This design workflow enables students to rapidly design algorithms in a manner that is currently used by industry. MATLAB and Simulink are currently used in industry to simulate, design, and control autonomous unmanned vehicle systems. It is also used to analyze large amounts of data that the unmanned vehicle systems produce. For example, BAE Systems Controls developed and successfully flight tested a UAV flight avionics system and ground control station in just 8 months, saving about 50% of their estimated development time. A few of you might understand what it is like to collaborate on code. The tools enabled BAE's geographically separated teams to design, model, and analyze the control system, simulate the UAV, visualize the simulation data, perform testing, and automatically generate the autopilot code within a single environment. The Monterey Bay Aquarium Research Institute, or MBARI in California, uses autonomous underwater vehicles to rapidly survey physical, chemical, biological, and geological conditions from the ocean's surface to the sea floor. MBARI researchers use MATLAB to develop automated tools for rapidly analyzing and visualizing AAV data. Two of the most amazing unmanned vehicle systems that were developed using MATLAB and Simulink are currently on a different planet. JPL engineers used MATLAB and Simulink for numerous phases of the Mars Exploration Rover or MER mission, including navigation, data analysis, and the Entry, Descent and Landing or EDL system design. Prior to the rover's 7-month journey, navigation engineers had to prove that the rovers would make it to the Martian Gusev crater and the Meridiani Planum landing sites. JPL built a simulation tool with MATLAB that took into account the various attributes of the Martian surface to make sure that the chosen landing sites could be reached. With the rovers in full operation, MATLAB is used to reconstruct the data, to analyze the mission's performance, and understand the behavior of the various systems. Scientists are also using MATLAB to understand more about the geological data that the rovers are collecting. This visualization was created by Doug Hull and placed on the file exchange. It uses the recorded telemetry data to visualize the vehicle as it landed on Mars. As we have just seen, this EDL is a 3-stage operation that includes entry into the Martian atmosphere, slowing and controlling the descent through the atmosphere, and landing the craft safely and precisely. It is one of the most challenging stations of the mission. A combination of both MATLAB and Simulink were used to simulate this procedure, resulting in successful landings for both vehicles. For more information, check out the following user story called Bringing Spirit and Opportunity to Mars. So what is model-based design? With model-based design, you combine dynamic models, sensor models, control algorithms, and deployment implementation in a system-level model of your process or machine. So the key to model-based design is that you start with a Simulink block diagram or MATLAB simulation that mathematically models a system behavior. In an unmanned vehicle system, this model would provide dynamic models of the vehicle and its environment, sensor models, controllers, and a path to development. Here are 2 examples of mobile robot simulations that can be used in model-based design. These simulations can be found on the MathWorks file exchange. Both simulations model the environment, vehicle's dynamics, and sensors. The user is then able to work on various path planning controllers rapidly in simulation. This MATLAB-based simulation was built for the Control of Mobile Robots Georgia Institute of Technology course and Coursera MOOC. In the course at Georgia Tech, students were required to prove that their controller worked as expected on the simulator before trying it out on the hardware. In the MOOC, the simulator enabled the professor to remotely teach students all around the world how to control mobile robots. Here's an example of a Simulink-based mobile robot simulation that can be found on the MathWorks file exchange called Mobile Robot Simulation for Collision Avoidance with Simulink. This simulation was used for the MathWorks webinar, which has the same name. As of R2015A, you can also use the MATLAB ROS connectivity from the Robotics System Toolbox to design and test your MATLAB and Simulink mobile robot algorithms in the ROS-based Gazebo simulator. In this simulation, a MATLAB app is sending motor commands to Gazebo using ROS messages. Gazebo then simulates what a Turtlebot would do if it were given those motor commands. Gazebo then transmits camera and LiDAR data using ROS messages to the MATLAB app, where it is visualized. With model-based design in robotics competitions, we can start testing our algorithm design through simulation of the system model, early in the process without the need for a fully assembled robotic system. Although testing with hardware is very important, we do not need to wait for the vehicle to work before designing algorithms, if we develop a model of the plant and the sensors. Once the hardware is completely assembled and integrated, teams need a testing facility, which is not always easy to get to. Underwater and above water vehicles usually require a body of water, like a lake, which is hard to gain access to in the winter. With model-based design, we don't need to wait for spring before testing algorithms for this vehicle. We can test our complex control logic by simulating various operating conditions and failure scenarios. Imagine being able to ensure that your algorithm can handle any situation. If we are navigating through a field of obstacles, we can place these obstacles in various configurations to make sure that our path planning algorithm does not fail. If we're looking for objects of a certain color, we can vary the amount of light in the image to make sure that the image processing algorithms are robust enough to handle the lighting conditions. After designing the algorithms, we can then run MATLAB and Simulink directly on a desktop computer to control our AAV. We could also generate code out of MATLAB or Simulink to deploy to a desktop computer, microcontroller, or FPGA. In all of the AVSI Foundation competitions, I've seen plenty of teams use MATLAB to simulate and deploy path planning algorithms. In Robot X, a team obtained 4th place by building a simulation in MATLAB in which their vehicle identifies obstacles and performs path planning. After simulating their path planning algorithm in MATLAB, the team then created an executable out of their MATLAB code, which they placed onto a desktop computer to deploy their algorithm. Another team that obtained 3rd place in the Robot X competition used MATLAB to design and simulate acoustic and image processing algorithms. After simulating their algorithms in MATLAB, they then used MATLAB ROS to deploy their MATLAB algorithms as a ROS node in their vehicle's ROS network. This node was run on a desktop computer to deploy their algorithms as well. To learn more about model-based design for unmanned vehicle systems, check out the Model-Based Design section on the MathWorks AVSI page. You can find the MathWorks AVSI page at the following location. And that is the end of today's session. So if you want to have a look at all the MATLAB and Simulink videos for unmanned vehicle systems, navigate to the dedicated web page shown here. If you want to get all the information about AVSI Foundation activities, go to the dedicated MathWorks AVSI Foundation webpage. And if you have feedback on the episode, things you like, and topics you would like to see, please let us know by sending us an email at avsifdn@mathworks.com. For those of you that don't know, we have a complimentary AVSI Foundation software offer. You have free offline access to all the software that we use here in these videos. Thank you for watching, and see you next time.